Okay, so we're going to start the video on hypothesis testing. And we're going to start off with a few basic definitions about what we're trying to do with hypothesis testing. So we have a null hypothesis, which is the current state of being. And we have an alternative hypothesis, which is what we're trying to prove. So to maybe give a very silly marketing example, we're going to say that, you know, the color of the drink does not affect a kid's enjoyment. So if we have exactly the same tasting drink and like one is blue and one is red and one is green, um, people if you give the child a drink, their enjoyment of the drink should not depend on the color. Um, but what I want to prove is that maybe some behavioral effect, if somebody looks at a bright green drink, is going to affect how they perceive the drink, and kind of almost moderate some of the taste, the taste response. So my alternative hypothesis is it is going to affect people's taste perception. So here, the color of the drink is my what we call the independent variable, our experimental variable. And what we're going to try and measure, our dependent variable, is the children's taste response. And that can be measured in different ways, probably through a survey. How much do you like this drink from 1 to 10? But we could also have things like biometric response. Um, this is a little bit narrow, a statistical hypothesis, because we can have things that are not necessarily numeric values. So hypotheses can be quite general. So I'll give you a general example, and then I'll give you a few kind of numeric examples. Okay, so off to the whiteboard. So let's just kind of have a bit of definitions. But first, we've got to get our pen ready. So usually we refer as like a shorthand would be H0 would be the null hypothesis. And HA would be the alternative hypothesis. And I will fully admit I'm a little inconsistent in whether I use a big A or a little a. So just pick whichever one you like the best. It really depends on the textbook, and then kind of go with it. So let's think of an example. And I always worry about this because most international students have never seen American football, but I hadn't seen much American. I'd seen a bit before I came to the US. But basically, in American football, you have a touchdown, and usually it's reviewed. Once people score a touchdown, it's reviewed by extra video referees, and they will try and gather evidence that it's not in fact a touchdown, that maybe somebody stepped outside the line, that they didn't handle the ball properly. And that's really what hypothesis testing is. You have the null hypothesis, and it's a process of gathering evidence to prove the alternative hypothesis. Just like if a detective is trying to prove somebody's guilty of a crime, at the beginning we don't have any evidence, so the null hypothesis hold they're not guilty of a crime, but we can gather evidence and prove the alternative hypothesis that they have committed a crime. So let's have a little example. So H0, the referee's decision was correct. The original referee's decision was correct. And it is a touchdown. And the alternative hypothesis, the referee's decision was not correct. It is not a touchdown. So let's do a few little things. Um, let's do a few numeric examples. And we'll stick with kind of simple. We'll kind of get more complicated as um, the class goes on a little bit, but we'll stick with kind of looking at, one value at the moment, which is one sample. And as the class goes on, we'll get with more and more kind of complicated variants. So let's just do H0. Imagine that we have, some sort of standard in our company that the average competency score should be at least 70 out of 100. And we can say the average competency score is 70. And HA will say the average score and I'm going to do three variants, is not equal to 70. Let's move up a little bit. Um, is less than 70. And is greater than 70. And we kind of, here we're looking on both sides, and on the next two, we're looking on just one side of the null hypothesis. So I'm going to do this numerically in a minute, but this is what we call two-tailed. And this is what we call one-tailed. And when I present these examples, kind of as I do in an undergrad class, um, we would kind of have, this would be our scientific or our business hypothesis. I usually call it a business hypothesis in this class. Kind of the wordy version. And then we have a statistical hypothesis. Where we're dealing with the parameter, with basically we're making inference on a population parameter. But before we're going to build this in a little bit more math in a minute. We just got a few little additional definitions. And the first of these is a type 1 error. So this basically is we reject the null hypothesis in favor of an alternative hypothesis, but in fact the null hypothesis is true. So we got it wrong. So in my little example, if I make a type 1 error, I'll say, yes, changing the color of the drinks does change the taste perceptions, but in fact it doesn't, so I made an erroneous error. A type 2 error is kind of the opposite. So maybe changing the color does change taste perceptions, but in fact, I can't find that effect. I can't gather the evidence. So I said, no, there is no change, but in fact, there is a change. So that would be a type 2 error. So let's just actually look at the little table And let's just do that with our kind of touchdown example. So I'm going to go, let's just do full screen here. Here we go. And so imagine that we have our little touchdown example kind of side by side here. And we're going to write with red pen. Okay, so let's just think what this is our actual conclusion. And remember I said the H naught on the touchdown example is it is a touchdown. So we basically say, yeah, we accept the touchdown. So we conclude we accept the touchdown. And here we overturn, we reject the touchdown, so we overturn it. We'll go a bit out there. But in fact, so this is the true state of nature. So this is the true. H0 is true. So it is a touchdown. But here HA is true. So it's not a touchdown. Sorry, this is a bit squashed. So if it is a touchdown and we accept the touchdown, we don't overturn it, we've made a correct decision. And likewise, if it's not a touchdown and we overturn the touchdown, then we've also made a correct decision. However, if it is a touchdown, H0 is true, but we overturn it, then we've made a type 1 error. And conversely, if it's not a touchdown, but we accept it, we don't overturn it, I get fired as a referee, and also we've made a type 2 error. Now notice that the probability of a type 2 error is called beta and the type 1 error alpha. Don't worry about the beta yet, we'll cover that in a few weeks' time. The key is here with hypothesis testing is we kind of define the strictness of our test with the alpha. So the alpha basically says how much evidence we need to actually have. So the alpha is kind of quite a key condition in the strictness of the test. And this is what, whenever we say, we'll be doing a hypothesis test, we set our alpha. This is setting how tough our test is, how much evidence we need to overturn the null hypothesis. So we'll go back to our other board. And we're now going to define, I'll keep this up here because it's that example, we'll define some of our numeric information. So let's just do this. Why it always goes back to select. So we have our population parameter mu. And so our null hypothesis is mu equals mu0, our hypothesized value in these tests. And in this case, mu0 would be 70. So we would have H0 mu equals 70. What you don't want when you're defining a hypothesis is you don't want any sample values. I see even PhD students making these errors. You don't want to have an X bar in your hypothesis. That's not meaningful. We're making the hypothesis about the population. We're not making the hypothesis about the sample. Now, again, going back to our two-tailed test, looking in both directions, we have HA mu is not equal to mu 0. Okay, let's move up a little bit. And we'll have, this is the two-tailed variant. And we also have the one-tailed lower. So my pen has all these weird buttons on them. And the upper. Here we're just looking on either side. Oh, my computer's just slowing down here. And these are the one-tailed tests. So how do we implement this? Let's go back to our old friend, the sampling distribution. But this time, a key thing with the hypothesis test is, let's just say, I want to write this down because this is like very important. I'll put important in big letters, I'll shout it. We assume H0 is true. So we use the H0 distribution. And in fact, what we're doing is we're basically collecting a sample. So we collect sample. So we collect our sample values. Our X bar is our mean. S is our standard deviation. And obviously, width is on a sample of n. And these are called sample statistics, i.e. we're doing statistics, which is a statistics class. So imagine we have a sample distribution, but H0 is true. So we're going to draw our little sampling distribution. But we have H0 is true. So if H0 is true, we're going to be centered at mu 0. And you can see we have all these, all our X bars. It's still a sampling distribution, but it's centered at H0. Now, the first thing we want to do to make it easier, because when these tests were invented, they didn't have Excel or computers. We only had the standard normal tables at the bottom of the textbook, is if we have a value of X bar, so we have our sample mean, for example. So imagine that we get a sample mean. We want to transform it into a z-score. So we want to transform into a z-score. So we have our z-score here. Now in a z distribution, of course, we're centered at 0. And we have a standard error of 1. So we're going to do z equals, we want the center to be 0, but previously it was mu 0. So we do X bar minus mu 0. And then we divide by the standard error. So this has got as a normal, it still has, even though it's now been centered at mu 0, it's still got this standard error, which we could, as with the confidence intervals, we sometimes have to estimate that. So we're going to do that. And that's our Z transformation. And what we're doing with the test is we want to see, to reject our null hypothesis, we want to see if we're far enough away from the null hypothesis to reject the null hypothesis defined by our type 1 error. So the type 1 error, let's just assume this is a one-tailed test. So we'll assume that, we're doing it's easier in one direction. What we want to do is we want to actually show that we're far enough away that we're in this error region of alpha, our type 1 error. So all alpha is doing is controlling our strictness. If alpha is smaller, we've got to go further and further away to have evidence of rejecting the null hypothesis. And this is known as the rejection or the critical region. Now, I admit to, again, I've been called out for this before. Different textbooks, some people call it the rejection region. Other people use the critical region. I'll try to be relatively consistent on this. So just give me a second. Okay, I just wanted to make sure what I was using in the slides, and it was, I've been using the rejection region. So this is really what we're doing, and now we're going to kind of formalize it as the different types of tests. So this is going to be, oops, didn't want to do that. I wanted to draw a line under this and say we're now going to give the formal definition, which is kind of what we're going to finish with today. And I'll start off, quickly review this, and then we'll get straight on to some numerical examples. So we have a one-tailed test where the null hypothesis is, somehow my computer doesn't like statistics. It's just slowing down. And we're testing only to the left or potentially to the right. Or we can have a two-tailed test where we're testing in potentially either direction. Now, we actually can now do the actual test. And remember, all we're doing is we're taking this sample mean, and we're putting it on. So this is kind of the hypothesis. I should have written it there. So this is the hypothesis. We now have the test statistic. And all we're doing is we take our sample, we get our sample mean, we get our standard deviation. And basically what we're going to do is we're going to do Z, as I showed you there, equals X bar minus mu 0 all over sigma over root n. But we don't, we rarely know this. Because again, if we know the population standard deviation, we probably know the population mean, and there'd be absolutely no point in doing a hypothesis test. So we'll do Z equals X bar minus mu 0 all over S over root n. And now we define our rejection region. Where we reject the null hypothesis, i.e. And here, so we're going back to like one-tailed and two-tailed here. The z was the same for both of them. So the one-tailed, let's just do the lower first. So again, we'll draw a little distribution. We've got our sample mean turned into a z. We're looking to the left, so we're trying to gather more evidence to the f, to the left, until we get into this alpha region, the type 1 error region. And we define our rejection point. We'll use a z star as the critical value of z. And, we start off in the middle and we're assuming the null hypothesis is true. We gather more and more evidence until we reject. And we reject H0 if our z value is less than our z star. Okay. So the next one, we're going to do the upper. And this time, we're testing if H, we're testing to the right. And again, start off in the middle. We've transformed into the our sample mean into the z distribution. We're trying to gather more evidence until we kind of hit this thing. And we're going to reject H0 if z is greater than z star. And what we usually do is we'll usually define this. We'll actually call this z star alpha. So it's basically greater than z alpha. So again, this is the type 1 error. Now, two-tailed is a little bit different. I'll draw this bigger. Here we go. And this time, we still have to have alpha, but we're looking in both sides. So what happens is we have alpha over 2, alpha over 2. So this means this is going to be z star alpha over 2. Oh, sorry. I should say z minus z alpha. This is usually, as we have the alpha, this would be minus z alpha, and this would be positive z alpha. Sorry about that. And that's minus z alpha over 2. And again, if you have some textbooks would actually use this is why it can be confusing. Some textbooks would have z alpha over 2, z 1 minus alpha over 2. Yeah. Again, going from left to right. But we're going to use minus z alpha over 2, z alpha over 2. And let's move up a little bit. We're going to reject H0. If the absolute value of z is greater than Z alpha over 2. Now that just basically means it encapsulates two things. It's like Z is less than minus Z alpha over 2, and Z is greater than Z alpha over 2. I think that's why the book uses this kind of notation, because it's for kind of maybe undergrads, it's actually easier to think of minus in one direction, positive in the other, and we have symmetry in the middle. But this is kind of what we would do, if we were doing a math stats class or if we were doing Excel, we would be doing that. Okay, so just a summary. One-tailed test, we're looking in one direction, either lower or upper. Two-tailed test, we're looking in both directions at once. We're just gonna, the best way to learn how to do this is just to do examples. So we'll start off next class with examples. And I'll also show you a different conceptualization. I'll talk a little bit about p-values and how they relate to hypothesis tests. Okay, so that's